You are literally being crushed by the weight of sunshine, and every time you step into a shadow, you are physically losing weight. Let's talk about the weight of nothingness. We've all played with hand shadows, creating dogs, birds, or strange shapes on a bedroom wall. But have you ever stopped to wonder about the physical cost of that darkness? It sounds like a question pulled from a fever dream. How much does a shadow weigh? At first glance, it's a total non-starter. A shadow isn't a thing, it's an absence. It's the void left behind when an object decides to get in the way of a photon's journey. You can't put a shadow on a scale, you can't bottle it, you can't weigh nothing. Or can you? To understand the weight of a shadow, we first have to accept a terrifying reality. Light has mass-like consequences. While photons themselves are massless, they carry momentum. They are tiny, invisible bullets of energy. And when they hit something, they don't just illuminate it, they push it. Think about that for a second. Every time you walk outside on a bright summer day, the sun isn't just warming your skin, it is physically shoving you toward the pavement. On a global scale, this light pressure is staggering. On any given sunny day, the city of Chicago, with all its skyscrapers, deep-dish pizza joints, and millions of people, actually weighs about 300 pounds more than it does at night. Not because of the air, not because of the humidity, but simply because the sun is pressing down on every square inch of the city, with a force of about 1/1000th of a pound. It's a microscopic force on a human scale, but on a planetary scale, it changes everything. This brings us to a mind-bending realization. If light adds weight, then the absence of light, the shadow, must technically represent a loss of weight. By standing in the shade, you are shielding the Earth from the sun's physical pressure. You are, in a very real, calculable sense, making the ground beneath you lighter. But if light is a physical hammer, and shadows are the relief from that hammer, how far does this rabbit hole go? If we can weigh the sun's impact on Chicago, can we see the shadows of objects that aren't even bright to our eyes?
In the vacuum of space, where there is no air to cushion the blow and no magnetic field to shield the impact, the weight of light stops being a fun trivia fact and starts being a navigational nightmare. If you're a rocket scientist at NASA, planning a trajectory from Earth to Mars, you can't just account for gravity and fuel. You have to account for the sun's shove. If we ignored the physical pressure of sunlight, a spacecraft traveling to the red planet would be pushed over 1,000 kilometers off course. That is the difference between a successful landing and drifting into the cold, silent abyss of the solar system forever. We have even learned to harness this weightless force. We've built solar sails, massive reflective sheets that act like the sails of an ancient galleon, but instead of catching the wind, they catch the relentless bombardment of photons. The sun isn't just a lamp, it's a cosmic engine. But let's bring it back to the shadows. If light is a physical force, then the shadows we see are regions of lesser pressure. On Earth, we are used to two major shadow casters, the sun and the moon. These are the obvious ones. But there is a third celestial body capable of casting a shadow on Earth sharp enough for the human eye to perceive. Can you guess it? It's not Mars, it's not Jupiter, it's Venus. Astronomer Pete Lawrence proved this using a digital sky and a specialized tube. By isolating the light from Venus and passing it through a cutout of the astronomical symbol for the planet, he was able to project a Venusian shadow. It is faint, haunting, and incredibly rare, but it is physical proof that even a pinprick of light from millions of miles away carries enough energy to define a shape against the darkness. This leads us to a fundamental realization. Light is the protagonist of our universe. It dictates weight, it dictates visibility, and most importantly, it dictates the universal speed limit. We all know the magic number. C equals 299,792,548 meters per second. That is the speed of light in a vacuum. It is the fastest anything can possibly go. Or is it? You see, there's a loophole. The light hitting your eyes right now, the light coming off your phone or monitor, is actually breaking the rules. It is moving slower than C. Because while the speed of light in a vacuum is a hard limit, the moment light enters a medium, like the air in your room, the water in a glass, or the glass of your screen, it starts to lag. In air, light crawls along at a paltry 298,925,574 meters per second. And this slowdown creates a window for something truly impossible to happen. It allows matter to do the unthinkable, to outrun light itself.
If c is the universal speed limit, how can anything outrun light? Here is the secret. While nothing can travel faster than the speed of light in a vacuum, particles can outrun light when it's traveling through a medium like water or glass. When a charged particle, such as an electron, tears through water faster than light can navigate that same water, something miraculous happens. It creates a photonic boom. This is mathematically and physically analogous to a sonic boom. In a sonic boom, an object travels faster than the sound waves it's producing. Those waves of air pressure can't get out of the way fast enough, so they bunch up, overlap, and create a massive, explosive shock wave of sound. In a medium like water, the molecules become polarized by the passing particle. Normally, the photons they emit would just drift away and cancel each other out. But when the particle is moving faster than those photons can travel, the light waves begin to constructively interfere. The result? A haunting, ethereal blue glow known as Cherenkov radiation. You can see this in the cooling pools of nuclear reactors. It is the visual signature of the universe's speed limit being challenged in a local race. But this isn't just something happening in labs or reactors. It has happened inside the very bodies of explorers. Astronauts, particularly those on the Apollo missions traveling to the moon, reported seeing strange flashes of light even with their eyes closed. For years, this was a mystery. We now believe these flashes were caused by high-energy cosmic rays, charged particles, shooting through the liquid inside the astronauts' eyeballs faster than light travels through that liquid. They were seeing photonic booms happening inside their own heads. Now, let's pivot to a thought experiment that many of you have asked me about. It's the ultimate life hack to break the laws of physics. Imagine you want to push a button that is exactly 1 light year away. We know that light would take a full year to reach that button. But what if you built an incredibly rigid board, a massive 1 light year long wooden plank reaching all the way from your finger to that button? If you push your end of the board now, doesn't the other end hit the button instantly? Did you just send information faster than the speed of light? Did you just break the universe? The answer is a definitive, mind-bending no. You see, we are no longer talking about the speed of light. We are talking about the speed of push. When you push an object, you aren't moving the entire object as a single, indivisible unit. You are pushing the atoms at your end of the board. Those atoms then push the atoms next to them, which push the next, and so on. This information that a push has occurred travels through the material as a compression wave, and compression waves in a solid material travel at the speed of sound within that material. If you pushed a light-year-long board made of steel, the other end wouldn't move for decades or even centuries because sound travels much, much slower than light. The board would actually compress like a giant spring, and the push would slowly crawl its way across the vacuum of space. To us, in our daily lives, pushing a chair or a door feels instantaneous because the distance is so small and the speed of sound in solids is relatively fast. But on a cosmic scale, the speed of push is a snail's pace.
If you want to see this delayed reality in action without building a light-year-long wooden plank, you don't need a space station. You just need a slinky. In a famous experiment popularized by Veritasium, if you hold a slinky vertically and then let it go, the bottom of the slinky does not move immediately.
Gravity is pulling on the whole thing, but the bottom of the slinky stays perfectly suspended in midair, defying gravity for a fraction of a second, until the information that the top has been released reaches it. This information travels through the slinky as a tension wave, a physical message telling the bottom, "Hey, we're falling now." Because the slinky is so elastic, that wave travels slowly enough for our eyes and high-speed cameras to see. In a light-year-long board, the same principle applies. The universe is not a rigid place. It is a giant cosmic slinky. So, where does that leave us? We started with a silly question. How much does a shadow weigh? Through the lens of physics, we've discovered that this question isn't silly at all. It reveals a fundamental truth about the mechanics of our reality. Shadows have negative weight because light itself is a physical burden. Light pushes cities like Chicago with the weight of a few grown men. Light dictates the path of our most advanced spacecraft. Light creates sonic booms inside the eyes of astronauts. But for all its power, light is also a tether. It sets the speed at which we can see, the speed at which we can move, and the speed at which we can push back against the void. You are technically heavier when the lights are on. You are being pelted by trillions of invisible, massless hammers every second you spend in the sun. The next time you're walking on a sidewalk and you see your shadow stretched out before you, don't just see it as a lack of light. See it as a relief. In that dark patch of ground, the Earth is taking a break. It is shedding a tiny fraction of its weight, shielded by your body from the relentless, heavy pressure of the stars. The universe is heavy. The speed of information is finite, and even the smallest shadow is a testament to the incredible, crushing power of the light that surrounds us. I've put links in the description to the deeper physics of solar sails, Cherenkov radiation, and the slinky effect if you want to fall further down the rabbit hole. And as always, thanks for watching.